Okay, so today is the third session. Just as always, just a few practical things. Just a reminder that next week RosBREED has its yearly meeting, so I won't be able to give a session, and the week after that I'll be traveling, so I also won't be able to give a session. And after that, for the people in the US, nothing will have changed, but after that, for the people in Europe, you will have switched to daylight savings time, so that means that the sessions will be taking place an hour later again, just as they were in the first week. Then I've been getting several questions whether the recordings were available. Given that we didn't find any other solution, I decided to post them on YouTube, so they're available now for the first two sessions, and then today's session I'll probably make available a bit faster than the last two, so that should be in the next few days, and I'll send an email around when that video is online. Right now it's just a video. I do plan to get some table of contents online with the video that shows you at which point a certain part of the workflow starts, so you can more easily navigate to that. And later, I hope I can split up the videos into smaller ones so that each section just is a single video rather than having a 1 hour and a half or 2 hour video. And then for those who were not here last week, there are backup files, and the backup files are meant in case something goes wrong along the way during the session, either for me, but I hope nothing goes wrong for me, or with your files or your software, and then at any point you can just keep picking, take the files that are available to you, and then figure out what went wrong afterwards. And if you cannot find a solution, you can always contact me and we'll figure it out together what's going wrong. So then for today, we're at the third session. So the last just a reminder, in the first session we talked about why curation is needed, and we loaded our data into Genome Studio and had a first look at it. And then last session we went over a lot. We checked our individuals, we checked the quality of the results per individual. We also checked whether they are diploid or polyploid. And then at the end we used assist to find a subset of markers that were working reliably. And today we'll be using that data to find duplicates in our data set and to make sure our pedigree works. But before I start with that, I want to go back to assist for just a short little bit, because at the end I said we can export our results in assist. So after selecting our files by clicking on this button, after setting our parameters, and after running assist, we got here, and then I quickly mentioned that we can export our results and that there's several files that assist can create. And at that point I said I also wanted a Plink file and a FlexQTL data prepper file, and I pointed out and I told you that we could fill in here a name and that all the files would have that name plus something extra. So I want to just come back to those files that assist creates quickly so that you have a better idea of what it's creating. So for those who weren't able to run assist or who weren't there last week and haven't been able to run it, now they're in the backup files. Under session 2 there's a folder called assist output, and that has an example of many of the output files. If you did run assist, I saved mine last time under Genome Studio Output. I've now moved them to a folder called Assist Output. And here are similar files. And so one of the files Assist makes, or that you can create with Assist, is a summary file. I'll go ahead and open that one. And so the summary file just gives a summary of everything you did, because as I mentioned last time, you cannot save your run or your project in Assist. So once you close Assist, everything is lost. And so by saving a summary file, you can see what you did to get to these results. So it's saying which input files, it's telling you which parameters you used and which values you used, and then here it says which files were created, and then it gives here the summary of the results, which says there were 2,180 SNPs approved, of which 1,446 were robust, and the 734 other ones were distorted and showed an unexpected segregation, but Assist figured they were still working. And then there were a whole bunch of discarded SNPs. And if you remember from last time, I said, well, the ones in the shifted homo group are probably, there's still a lot of those, are probably good. So that's one of the files Assist creates. The other, this one, the G types and file, is another file that's important. And I wanna, because what it does, it gives you the genotypes for all the individuals and for all the SNPs that it called reliable. So this only lists the SNPs that it retained, and not the ones it discarded. There is one thing I want to point out here is you can see that there's in column L and M, there's 2 individuals, but they don't have any data. Now, if I go to the end of the file and I'll just click on any cell on the top row and hold Control and press right, which moves me all the way to the end of the file, you can see now that there's here 2 columns which don't have any data, that have data but don't have any name. And so that's a little mistake, I think, in the Assist output, where it creates these 2 empty columns. So if you want to solve that, you can highlight those 2 individuals, right click, and after you've right click, you go to Insert, and you make sure you choose Insert Cell or Shift Cells Right, and by doing so you will move those 2 cells, and then everything should be okay, and then you can go ahead and delete those 2 columns. The other thing I want to point out here is that Assist does not use the A-B format. It changes the calls to A, C's, and G's. If you go through this whole file, there's not a single T, so I don't think it's doing necessarily correctly saying for each SNPs which the 2 nucleotides are. You can easily change this back to the A-B format by selecting everything, and selecting everything, I just click on the first cell that has a genotype value, holding Control and Shift, pushing down and pushing to the right, and then you have everything. And by then pressing Control H, you get to the find and replace, and you can replace all the possible options by ABs again. So AAs would stay AA, ACs would become AB, AGs would become AB, and then CC and GG would become BBs. I'm not going to do that because that might take a little bit, and I can work with this file like this for now, but it might be useful because at that point you can start comparing these results again to the ones you're getting from Genome Studio. And one more thing I would like to point out is if I look at all the possible values here, there's also a few that are DD, II, and ID. And I think those stands for insertion and deletions, and I am not really sure how assist gets that idea that where there's an I or a D. I haven't really looked into that, but so there's a few of those as well in this file. I'm gonna save this because I'm gonna use this file later again. And then there's some Blink input files that I've asked for. There's a FlexQTL data prepper file, which we will use next session. And then there's the SNP info table, and if you open that, what this file does is it gives you the SNP names. It says what the position of the chromosome were based on the map, but the interesting thing here is it's giving us the classification of each SNP, and this is for all the SNPs, so also for the failed ones, not just for the ones that it thought were successful. And actually this information is really interesting to have in Genome Studio, and to get this into Genome Studio, I'm going to highlight, or I'm going to get those two columns, the column with the name, and then I'll hold Control down and I click on column E to get the classification. And I'm first going to copy those into a new sheet. So by clicking here at the bottom, I'm just going to open a new sheet and get all this data in here. And then I'm going to copy it again and open Notepad. And copy those two columns in. If I hadn't copied them first to this sheet, and I would have just copied them as they were here, then in Notepad you would have added these three columns as well. And we don't need those columns, so I wanted to just not have them, and because I don't want to have them, I first went to this sheet before copying everything. Now in Notepad or in Excel, I have to do one more thing, which is go all the way to the top. And this one says SNP ID, and it has a space in here. And Genome Studio needs to know that it already has this first column in its table. And in Genome Studio, this one is not called SNP ID, but it's called name. So I'm going to change this to name so that Genome Studio will now know that it needs to compare this column with the names when it's loading in this data. And then I go ahead and save this. So I press save. I'm going to save it in the assist output file. And I'm just going to call this SNP classification. And then I'm going to hit save to save this as a text file. And then I'm going to go to, at this point I don't need to save it anymore because, well, one, this is a CSV file, so it will not remember two sheets, and I don't really need this anymore, so I'm going to not save. I'm going to say yes to that. And so then if we open Genome Studio and we ignore the error because I just get it sometimes, I don't know if anybody else is getting it, but Genome Studio seems to be working fine. I'm just going to open the project we've been working with by double clicking on it, and that should go quickly. So now we're back in Genome Studio. As you can see, the individuals I used are still the individuals with poor quality are still excluded. And now I want to import that data, and importing the data, we go to the full data table which is the top right pane here. And the fourth icon is saying import columns. So if we click on that, we get a whole lot of information. What's important is that it uses tab delimited files, so that's why I saved this as a text file. And now I will look for the file, and I saved it in the assist output file, and I called it SNP classification. So once I have this file, I can go ahead and click open. Column import is the right one. We don't want it as a sub-column import. And then I go ahead and click on OK. And as you can see now, there's a new table or a new column in the full data table, which is telling me the classification of each SNP. And so from now on, when I'm looking in Genome Studio, I know how Assist classified it. And I can use, not just as any other column I've been filtering for, I can also start filtering for this column. And so I can have a look at those ones that, like I said, that I think are still good, and I think in this case, for instance, they are probably still okay. So that's how we get this information from Assist into Genome Studio. So then I'll continue with today's session about duplicates and pedigree. So we'll start with duplicates. So if you remember, there we had some known duplicates in our data, or in our germplasm. And so the first thing we can do is go and check how they performed, whether they actually are the same. So to do so, we're still in Genome Studio, and we go to Analysis at the top here, and we want the report, and we want the reproducibility report, or reproducibility and heritability report, and we want it with calculating the errors. And so if you click on that one, it will ask you how you want to call this. I'm gonna save this back in Genome Studio output, and I probably have one, but I'll just save over it. So I'll hit save. I'm gonna save over the old file, and then Assist will Genome Studio will do its evaluation of all the individuals and save the results in that file. And once this will be done, we'll get the question whether we want to see the file or not. And once you get that question, you can go ahead and click on yes. So here's the question whether we want to see it, and I'll click on yes. And I'll open this, and make some of these columns a bit bigger so we can see what's happening. So this report consists of 3 parts, and I'll highlight where each part starts. And we'll come back to those 2 parts a bit later today. But for now, let's focus on this one, which says duplicate reproducibility. And so we get here the report on how our duplicates worked. And so you can see that here we have Hedelfingen, duplicate 1, and Hedelfingen. And then it reports here a number of correct SNPs, which means how many SNPs had the same genotype call. Then here under errors, it lists how many calls were different between the 2 duplicates, and that's actual differences. It's not if one is a no call and the other is a call. It's really 2 different calls, so AA and versus AB, for instance. And then here it lists the total of SNPs, number of SNPs that it looked at. And so as you can see here, it's 11,500, whereas the array has about 13,500, which means there's about 2,000 SNPs Genome Studio did not look at, and that's because either one of the 2 or both individuals had missing calls for those. And so at that point it could not compare it. And then here the reproducibility frequency is really what is the proportion of good SNPs, or correct SNPs that are identical over the total number of SNPs. And you can see here that that is about 99.8%, which is really high, which is good, because that means that those two are indeed the same individual. Now all the other ones have 0, 0, and 0, and why is that? Well, because some of these individuals we excluded from the analysis because they didn't have good data. We didn't trust the results, and so those individuals we excluded don't have any genotype calls anymore, which means that Genome Studio cannot compare them. But if you go to the backup files for today's session, so session 3, under the Genome Studio output, there are two files that say that give this reproducibility report, but it says with low quality individuals. So I'm just going to show that to compare with the results we have for the other ones with the results we have now. And so as you can see now, when I run this without excluding these individuals, and the red ones, the ones that are highlighted in red are the ones with bad data, then you can see that we do get numbers. And there's a few things you can see here. Well, one, that the number of errors is much higher than for this one, and that is probably not because they're not truly duplicates. It's probably because the quality of the individuals in red is so much worse that there's a lot of calls that are incorrect, and that those lead to the errors. You can also see that the total number of SNPs compared is much lower, and that is again because a lot of these individuals just have a lot of no calls. By the way, you can also see here that the total number of SNPs compared for Heidelfingen is also lower, and that is most likely because these bad individuals have been influencing calls from other individuals and making the calling of some SNPs not as good as they could be because of this poor quality data. And then the final thing I want to point out here is that we get a report from Bing versus Bing duplicate, and then again from Bing duplicate versus Bing, and you see the results are exactly the same because it's the two same individuals that were compared. Now if I go back to the sample sheet that I used for this, and let's wait till that. You can see here that this is the replicate column. Under the replicate column, for Bing I said it's Bing duplicate, and for Bing duplicate I said it's Bing. And that's why I said in the very beginning when we were making these files that it's probably just better to just leave for the original named individual, don't mention any replicate, because if we do, then we get these reports that are double rather than just a single report. So that is it for known duplicates. What I do want to show here are some more results from a larger germplasm, and you can see that overall we get pretty good values. And so I really think you should really be in the upper 99%, 99.5, 99.8 or higher even, to get for known duplicates most of the time. Although it could be a little bit lower, as we will see when we're looking for unknown duplicates. So when we're looking, why are we even gonna look further and look in our data set if there are any duplicates that we are not aware of? Well, one, the ones that we do know, we just want to check. Secondly, often with our crops, there's synonyms for, which means that genetically identical individuals might have a lot of names, and that is because germplasm is spread around the world, and as it is or was spread, it sometimes gets new names. And for instance, there's an apple individual called Duchess of Oldenburg, and you can see that there's a lot of other names for this individual, and they're all exactly the same. Well, for this one we know, but I'm sure there's a lot for which we don't know it, or that information might have gotten lost. So checking that is one of the first things we want to do. Secondly, we also have sports, and for instance in Apple we have Macintosh and Wajik. And Wajik is a sport of Macintosh, and it has a very distinct growth habit. It has a columnar growth, which, well, as the name said, it grows like a column, and so it's like it doesn't have any side branches, whereas Macintosh has a more normal growth type. And so that's a single change. But as we run our SNP array, it's very unlikely that with our SNPs we'll just hit that change. And so those two will also be identical. And then the last thing, well, finding identical individuals with an identical genotype call might help us find sample mix-ups. And I'll show you a few examples here of sample mix-ups. For instance, within the RosBREED data, we have Jonafree, which was originally called CoOP22, and it's completely identical to CoOP18. Now, it's been like that for any sample we've gotten, and we get our samples from the Geneva, New York collection. So this might mean that at the germplasm collection in Geneva, that actually those two are over there are identical, and so that something went wrong when creating this germplasm or when adding them to the collection. And in this case, it's most likely that Jonafree is true to type and not CoOP18. Also in Apple, in our RosBREED data set, we have 5 pairs of full SIP unselected seedlings that are genetically identical. Now, we don't expect seedlings of a family to be genetically identical. So that might either mean that something went wrong with sampling. For one of those pairs, though, they have been propagated afterwards, and they still are identical. And so, so that might mean that the issue is earlier. And what probably happened is that a lot of these seedlings were already grafted on a rootstock at the start of RosBREED or even before RosBREED, and so something might have happened there also with the grafting, at least for some individuals. Now, if you find sample mix-ups, you can just target both individuals again for genome scanning, just like you did with the individuals that showed any bad quality. Now, one of the advantages of finding duplicates is if that one individual has a no-call and the other doesn't, is that you could start filling in any missing data. Now, as long as your individuals are good, you won't have a lot of missing data, but it can help you to fill in some missing data. So how do we find duplicates? Well, so I got a question. Maybe the SNP array is not targeting all difference, and so the duplicates are not really duplicates. Yes, that could be true. Although most of the times these arrays that we use have been created for the germplasm we're using, and so they should be able to identify the differences. Where it might not be is when you start using wild material on these arrays, because they have a lot of SNPs that we never identified, and the SNPs that we identified in our germplasm might not be present in the wild material, and at that point you might get individuals that are looking very similar. But I think in my experience, as long as you're using germplasm that is related to the one that for which the array was developed, then they're probably, if you get a really high, if the calls are really identical, they're very likely to be the same. So in the cases of that I showed before with co-op 22. I'm sorry? So in these cases, well, Jonathan and co-op 18 are from different family, and so it's very unlikely that they would end up being identical. And even the full SIPs, it's very, very unlikely that they got exactly the same chromosome segments from their parents, especially because Apple in general is pretty heterozygous. So in these cases, I'm very sure that they're actually the same individual. But again, it depends a little bit on your germplasm, so you need to have an understanding of your germplasm as you're looking into this. All right, then on to, I hope this answered the question.
How do you deal with duplicate, or how do you find it?
Okay, so I'm going to show how are we finding new duplicates. The easiest, what I use is Plink, and Plink can be found in the software. But before we go to that folder, I want to get the Plink input files that Assist created. So I want to have both of the input files from Assist. So there's a Plink in map file and a Plink in ped, which stands for pedigree file. So I will copy those. And then I go to software, and under the ones that were copied to PC, there's a folder called Plink. And then within Plink, there's Plink 1.9. So you can see these files have already been pasted here, but I'll just do it again, just that we're all on this, doing the same. And then we want to run Plink, but Plink, unlike a lot of other software, if you would double-click this executable, I don't know if everybody saw it, I'll do it again, but it just pops up a window and the windows close immediately. So this is not how Plink is going to work. We'll have to tell Plink what it has to do. And to do so, we need to open either a command center window here or a PowerShell window, and that depends a little bit on which version of Windows you are using. And to get there, you have to hold down Shift, and while holding down Shift anywhere in this folder, you right click, and that should give me. No, it's not doing.
It didn't.
It didn't. So normally, yeah, here we go. I don't know why I didn't do it, but I hold Shift down, I click on right, and then I get Open PowerShell window here. Now you might not have Open PowerShell window here. You might have Open Command Center window here. I believe it is. So if I click on that, I get the PowerShell. People who get PowerShell will see this. The other people will see something like this, which is more or less the same. It's just all in black. So as you can see here, we opened this in this folder, so it's giving the whole path to this folder. And then what we have to do is slightly different between the PowerShell and the command window.
Pardon? There's a lot of stuff works through Linux too.
Okay.
Linux versions of a lot of these things.
Yeah, I'm sure.
But I'll show it for the PowerShell window, and then I'll come back to what needs to be changed for the command window. So for the PowerShell window,
Yeah, I mean, there's so much back and forth anyway, right?
Yeah,
from
to
Excel
to
I press dot and
Keynote Studio to Excel to
backslash.
We'll get to a little bit of our stuff.
Yeah.
More.
Yeah.
Is everything clear, or are there any questions? Because I hear I hear something in the background. I want to make sure I'm addressing questions as they arise.
I think that's us.
Okay. Goodness. Alright, so if we're in the PowerShell, you press dot and backslash, and then first thing we say is that we want to start Plink. So we have to say plink.exe to let this PowerShell or command window know that we are wanting to start this program. The second thing we need to tell it is to say which files to load. And we can do this by double dash saying file, having a space, and then say what the name of our files are. Now, in my case, it's 6 plus 9k. And then for my files, it's double underscore, and that's because when I created all the assist output files, I said it needs to be 6 plus 9k underscore, and assist automatically adds an underscore to every file name after that. So I get two underscores. Plink dot in. Now I don't have to say that it's a map and a path file. Plink is gonna assume it is, and Plink is gonna assume they have the same name. So I don't need to say anything else. So I don't need to specify what kind of file it is. I just need to give the name of the two files. Then next thing I'll tell Plink is what a missing genotype is. So that I do that by double dash missing dash genotype. I'll hit a space, and then the argument for this little comment is a dash, because that's what we have in the data set as missing data. And then I want it to compare all individuals against one another, and I do that by saying double dash genome, which makes Plink do this kind of comparisons. And I'm going to say full because I want to have everything compared with each other. Plink does a lot of other things, so there's a lot of other commands you could add to this if you want to run some other analysis. So for the people who have PowerShell, you can hit enter, and that should work. If you have a command window open, what you need to do is at the very beginning, and I think you can only move around this line of comment by using the arrows left or right, go all the way to the beginning and delete off the first two characters. So you don't need the dot and the backslash. And then you could hit enter as well, and it should run for you. So I'm going to add this in because I'm in PowerShell. And then if I do that, it says something that it cannot open this, and I don't know why it's not letting me open this. Oh, I know why. Because I made a mistake in my file name. It should have been underscore here, not a dot. And if I do it now, then everything runs. And since we only have 68 individuals, this goes relatively quickly. And at that point, Plink created a new file called plink.genome. And so this genome is the same as the command we've given. So this means that this is this indicates that this is where our results are. So in my case, my computer will already open this with Excel. I think for most of you it won't. So to get this open in Excel, you right click on it, say open with, and then for me Excel shows up. If it doesn't show up, there's an option to show more apps and find other software to open it with. If you still don't have Excel here, there is still another option to look for another app on this PC and find the Excel executable. I can show you where it is on my computer, if I remember, but it might be slightly different for different computers. So for me, I believe it's under the program files. Let me see. No, it's under Microsoft. In program files, it's under Microsoft Office. And for me, it was under root, if I remember correctly. And then under either one of these two, Office 15 or Office 16. And given that Office 15 is empty, it's under here. And then there's a whole bunch of folders. And at some point, I'll see excel.exe. And that's where it is. Now, it might not be exactly in the same place. So at that point, you have to look around a little bit in the Microsoft Office folders. Most people will also have 2 program files folder, so it might be in the other program files folder as well. If you cannot find it immediately, another way to open it is to go to Excel, click here on the top in File, and then you should have the Open option. You click on Open, and then we browse to the location of where this file is. And in my case, that would be under Software, Copy to PC, Blink, and then we don't see the file. Well, that is because here at the bottom it says all Excel files, and I want to change this to all files, and then all the files will show up. And then I can say open blink.genome with Excel. If I do that, I'll get a question here saying, well, the .genome is a tab delimited file. It's like a text file, and so Excel is telling me that it finds something that looks like columns, and it asks me how I want to deal with that. And I can say here I want delimited because I know which character is separating each of the columns. Then I hit next, and I say, in this case, it's not. I say I want space. And so now you will see that if I uncheck this again, this here at the bottom it still looks like this. Once I hit space, you'll see all these vertical lines go, and that's saying these are the columns. At that point, I can hit finish, and Excel will have nicely made this into a file full of columns for me. Now, for everybody who has it like this, you can leave it open. For those who right-clicked, said open with, and opened it in Excel this way, you will probably get something like this. And at this point, you can see that all the values are still just in the first column, and all the other columns are empty. So to get this into columns, you highlight the first column, which is A. We go to the Data tab, and under Data, there's an option to turn text into columns. And so we choose that, and at that point, it's the same steps as we've done before. If you would have opened it, rather as I showed you before. So at this point, we choose delimited, choose space, and then hit finish. And now we get again to this file where everything is nicely in columns. So, and then in this file, you have your 2 individuals, IID1 and IID2, that are compared. It's showing which germplasm or which family group it was in, which is one of the things you have in the input files of Blink, but Assist has generated those for you. And then the identity by state, so how much is actually they are identical, is summarized under the pi hat column. So in my case, for me right now, this is column K. But I'll have a quick look. So you can see these are about, here it is about 2,278 rows. So there's a lot of ones to go through. So rather than just going through all of them, I'll select everything so that, this data, that everything stays together, and I'll hit sort, and then you make sure that my data as headers is checked, so that because the first row in Excel are the names of the columns, and then I say sort by hat, and I want to sort from largest to smallest. And if I do that, we can see that at the top now we have Hedelfingen and its duplicate, and it shows us that it has a 99.8% identity between the two samples. And then everything below that has lower, much lower. So these two individuals, for instance, are only 86% identical, which is still a lot, but it's not a lot enough to say that they are truly duplicates. Now, this data set, as you may have guessed, does not have any other duplicates based on these results. If we go and look at some other results here, you see there's a lot of duplicates that have a high percentage, like 0.99. There's a few here. Here's a duplicate that has only 0.98, 0.9. And then there are a few that are even, then there is one that's even lower, which is 0.976, but we looked at it and they're actually identical. And then after this one, again, in this case, we have another big gap, which is here, 0.82. And I realized I made a mistake when I was saying it's 0.86. I should have been looking at this column, the pi hat, not at the distance. And so you see that the next one is only 0.66. So they're definitely not identical. Now, if you want, you can have a closer look at the rest of this table, because this is the identity by state, and it does not only show which individuals are identical. Well, let's see if I have this in the right folder here. Here we can also start looking at other relationships. For instance, we expect a parent and a child, or two full SIPs, to have an IBS of 0.5. Grandparents and grandchilds, we expect them to have about 0.25, half SIPs as well. So you can have a look at individuals that are around 0.5 and start looking at whether these might be parent-child or full SIP, etc. if you don't know about that yet. So there's more information than just the duplicates in this file. But as of now, we've at least for this data set, we found that there's no other duplicates than the one we already knew about. So I'm going to close this file. I'll save it. I also want to point out that if you should have a few triploids, you could, I've said before, let's get them out of our data set. You could check if you have duplicate triploids as well. Because their calls are also expected to always be the same, even though they're called as a diploid rather than a triploid. The only thing you have to be careful for is that A-B calls in triploids are not really A-B calls. They're actually AAB or ABB, and so having both an A-B call does not necessarily mean they're identical. Now, in this data set from Belgium, I had two pairs of triploids that were exactly identical. You can see here at the pi hat score that it was 1. And so to check whether they were true duplicates and to solve this AAB versus ABB, what I did is I exported their B allele frequency, which I still had from identifying them as a triploid, and I compared those. I compared those as well, and you can see that here. What this shows is, well, if it's an AB call, well, if it's an AB call and it was actually AAB, then the B allele frequency is about 0.33. Then it was the case for both individuals, and the same for when the call was actually ABB, then it's around 0.66. But it was also the case for both of these individuals. So the correlation was almost 1 between the B allele frequencies, and that showed that those two triploids were truly identical. So if you have triploids and you want to do a few more investigations on those, you can do that. Alright, and then we go on to confirming pedigree records. Why do we want to confirm pedigree records? Well, in everything that will follow after today's session, we'll be looking at errors based on inheritance principles, and those inheritance principles are that individuals inherited alleles from their parents and that alleles on the same chromosome are linked to each other. Now, if we have an incorrect pedigree and something is not the parent or not the child of another individual, we're going to enforce those principles incorrectly. And so at that point, we'll start identifying errors that are not truly errors. And we're going to look at them, and we're not really going to see what's going on, or we're not going to figure out what's going wrong with the SNP. And so we're going to lose a lot of time looking at that when we shouldn't even be looking at it because our pedigree was incorrect. Then secondly, when we're looking for these errors, it's not because a SNP has issues with its genotype calling that it will automatically give an error. In some families, the genotype calls will still all be right, and for those families, we won't see an error for that SNP. So the more data we have that can help us identify errors, the better. So the more parent-child relationships we have in our data set, the more errors we will be able to find if they are there. So how does pedigree checking works? Well, I think I've mentioned it already a few times, but I'll say it again. Each parent passes off one of their alleles to their offspring, at least in diploids. And so every parent must have at least have one allele in common with the offspring, and all the alleles that I find in an offspring or in an individual should be found in either one of the two parents. And so with those two rules, we can start checking whether an individual or a parent-child relationship and parent-parent-child relationship are correct. So I've already said parent-child errors. Parent-child errors. With parent-child errors, I mean that a parent and the child do not have any allele in common. So, for instance, the child is AA and the parent is BB. In that case, either that's an error in our calling, or there's something wrong with our pedigree, because a BB parent would have passed on one of its B allele to the offspring, and I cannot see that any of those B allele in the offspring. The same goes with SSRs. If a 292 individual cannot have a parent that is a 289, 298, because none of these two alleles occur in the offspring. Then when I say of a parent-parent-child error, what I mean then is I compare both parents to the child. So in the first example here, parent 1 can be a parent of this child because it has two A alleles and the child has an A allele. And the same goes for parent 2. But the combination of these two parents cannot have led to this child because this child has a B allele and neither of the parents have a B allele. And again, this is the same in the second example, where both parents share a 292 allele with the kid, but none of the parents has the 289 allele. So those would be parent-parent-child errors. So how do we detect them? Well, for B allelic markers such as our SNPs, it's really the homozygous markers that are informative. Because if a child is AB, then it could have anything as a parent. It could have AA, AB, or BB as a parent. So it's only the homozygous markers that give indication whether an individual can be a parent or not. For multi-allelic markers, it's both the homozygous and the heterozygous markers that could be an indication. Then once we go to the parent-parent-child errors, for both the biallelic biallelic markers and the multi-allelic markers, the homozygous individuals have already shown us whether an individual can be a parent or not. And I would suggest to only check pairs of parents when we when you first compare that, yes, the single parent can be, the single individual can be a parent. And so then by combining the information of both parents, at that point we've already looked at the homozygous markers in the individual, and we've ensured that that allele that is homozygous is present in each parent, and so that combination of those two parents will always work. And so it's the heterozygous markers that at that point will give us an indication whether or not the combinations of parents is possible. So there's a few ways of, well, first checking pedigrees that we know. And so I'll go back to the report that we created earlier to check for duplicates. So if you still have that file open, I said there were two more sections of this file, and these are the parent-child heritability and the parent-parent-child heritability. So as you can see here, for the parent-child heritability, Genome Studio is still comparing individuals, even if you've excluded one of them from the analysis, so you still get all these zeros here. But then in this case, Sunburst versus Summit, it's very similar to the duplicates, although obviously now it's not checking for identical SNPs, it's just checking whether the genotype call, the combination of the two genotype calls works as a parent-child relationship. But then again, it's saying for how many SNPs it worked, for how many SNPs it didn't work, and what the total of number of SNPs was that it looked at. And then in this case, again, it's giving a proportion of that, and we can see that for 99.9% of the SNPs, everything is working fine, which is a really good number. And so yes, Sunburst and Summit, this pedigree will have a parent-child relationship. Then in this part, it's looking at the parent-parent-child, and you can see here there's combinations here. So in this case, it's showing the individual and then the two parents. And you can see here that there's combinations like Benton and Stella that are not in this list. So Genome Studio will either look at this individual has only one parent in the data set, and I will report it under here, or I have both individuals in the data set, and then it will report it under here. Otherwise, it's very similar to before, and I will quickly grab just this subset of the results, and I'm going to sort this by going to Data and then hitting Sort. I again make sure that this is checked because I selected the names of the columns as well, and I'm going to sort it by frequency and go from largest to smallest and hit OK. And so now you can see here that there's a group of individuals that's higher, that has a proportion, these ones that are higher than 99%, and then you have a few ones that are lower. You can also see in the errors here that this number of errors is much lower than the number of errors for these last three individuals. So for all of these, I'd say yes, the pedigree is correct. Based on my experience in the crops I've worked with, I expect to have less, well, the amount of SNPs or the amount of errors that I allow would be somewhere around 0.5 to 1%. So anything with a proportion higher than 0.9 or than 99% would be okay. Anything below that is probably not a parent-child relationship, in my experience. Now, for these three individuals here, we then would conclude that at least one of the parents is wrong. Now, unfortunately, Genome Studio is not telling us which of the two parents is wrong. So if you want to use Genome Studio for that, you would have to go into Genome Studio and adjust the parent information, make one parent missing, then make the other parent missing. At that point, they would come up here. And that's a lot of work, especially if you have many individuals that that might not really have their pedigree correct. So there's other ways of doing that. I created an R script for that to check, and I will show that now. So for the R script, I need to go back to my assist output files, which can be found here for me, and I'm going to open this gtypes file that I showed earlier. So as you can see, I saved this. So because I saved this, these individuals now have their genotypes underneath them. And so yeah, if you don't, you still need to move you still have to move these two cells over to the right so that they have genotype data, and then the empty columns that arise from that you can delete. The way the R script works, it doesn't use individuals as columns. It uses individuals as rows. So for now, I don't need any of these columns, so I'm just gonna delete these for now. I will not save this file. And then I will get all the SNPs, names, and all the individuals, and go back up. And I do that by just getting the first cell of the table, and then holding Ctrl-Shift down and right. I select everything. I'll make a new sheet here. And then by right-clicking on the first cell, I get these options, and this time I would like to transpose the file so that rows become columns and columns become rows. And so by hitting that, I have now all my individuals in rows and all my SNPs in columns. Now, for my R script, I do need to know what the parents are, and right now it's not given in this data set. So to add the parents, I'll need 2 extra columns, one for each parent. So I'm going to highlight the top 2 columns, right click, and press insert to have 2 new columns. So now I need to get that parent information from somewhere, and I think that the easiest place to do that right now is in the assist input files, which for me were in the Genome Studio output files. And we created there a file that was called, which I indicated with pedigree because it was the pedigree input file for assist. So I'm going to open that with Excel, and I'm going to open that with Excel by right-clicking and saying open with Excel because it's a text file. And so this file for each individual holds both the parents. Now, as you can see, the order of these individuals is not the same in this file. The order of individuals in this file is not the same as it is in this file. But as in the first session, I told you about index match, so I'm going to use that function to pull out all the parents from the pedigree file into the genotype file. So I do that by clicking on the first cell next to Embruns, and I'm going to say equals to index, that's the first. And what do I want? Well, I want in this case, I want the mother or the first parent. So I'm going to, for this function, say look into the B column, because those are the values that I want. Then I'm going to hit match, or I'm going to say match, and I'm going to add the function match to the function in Excel here, and then I'm going to say, then it's asking me what's the lookup value. Well, what I want is the mother in this case for Embrun. And then then I need to say where would it find this value. Well, it would find that value in the first column of this file. So I go ahead and click on column A. And after that, I hit another comma and I say the last argument that I need is 0 because I want an exact match. And then I close off this formula. Now, if I could have been a little bit cleaner in the code, but if I drag this, you'll get an NA, and that's because now it's querying the 0 rather than Embrun for the second parent. So I'm going to say no, that it still needs to look for Embrun. And then the second thing is that it locked in which column to look in, and that was column B, but that would give me the mother again, so I need to change this to columns C. Now, if I had been a bit smarter about my dollar signs, I could have done this without having to change this formula. So once I have these two formulas in, I can select the two cells and then double click on this little square on the right bottom corner, and that should fill in everything. And so just if we can have a quick look, well, Embrunus, as you can see here, is nothing, so that becomes a 0. And we can go and look at Gilpack, and that does have Napoleon and Giant in here. So it seems that our formula is working. It got the right values. Now this is still a formula, and I want to get rid of the formula. So I'm going to select the first cell again, hold Shift down, press right to go one cell to the right and select that cell as well, and then hold Shift and Control down while pressing down, and then I'm selecting everything here. I'm going to hit Ctrl C to copy, and then if I click on the top left cell here, I can right click, and by right clicking I get these options again, and under the paste options I'm going to say values, because at that point my formulas will disappear. Now there's a few more things I would like to do. One is I'm going to change all the zeros to a dash. So I'm going to select both of the columns, column B and C, both columns that have the parents. And I'm going to say filter. And in this case, I'm going to, and then when filtering, it will look like this. I'm going to hit select all to unselect everything, and then select 0 here at the top to only get the ones that have a 0. At that point, I can hit a dash here. In case your Excel doesn't like it, because dash is also a minus symbol and it doesn't always accept it, you can hit the single quote and then hit dash, and then Excel should not give you any issue. And then, well, I can drag this all the way down. Oh, I have no idea why it's doing that. Okay, let me do that again. I can just, it's doing something I don't want to do. Alright, they should normally, okay, now it should work. And I can replace everything with a dash. Now I already see that all of these are also a dash, but I know there's a few more. So I'm gonna just clear the filter here, do the same for this column, make sure everything is unselected, and then select 0 to have only the ones that have a 0 here. And then I'm gonna do the same, and I'm just gonna drag this all the way to the bottom, so to make sure that all the zeros are now a dash. And then I'm gonna hit clear filter again, and then there's a few more things I need to do, and I'm gonna quickly check my slides to make sure I'm doing it correctly. Yeah, so the R script will expect the following 3 headers for these 3 columns. The first one is IND, or in for individual, and then parent 1, no spaces, and parent 2. And they should have a capital at as the first letter. So then I can go and save this file as And as long as I save it as a CSV, and as long as I do this correctly, I will only save the active sheet, and with that I mean it will only save this one and not the original sheet. So I'm going to make sure that I'm back into this one. I'm going to hit File, Save As. I'm going to browse where I want it saved, and I am going to save it with the R script, because I will use this as the input of my R script, and it's easier when this is in the same folder as the script. So that would be under the software folder and then in the R scripts. So you can see I already have a few files here. I'm just going to overwrite this parent check file. I'm going to save it like that, and then I'm going to hit save, and I'm going to replace it now. So I'm going to get this question saying that it's multiple sheets and that I'm okay to only save this one, and yes, I'm okay with that. So if I then go to the folder with the R scripts, which again is under software, R scripts, then there should be a parent check R script here, and this is the file I just saved, and I'm just going to double check that it looks good, and it's already opened, and yes, it looks exactly as I want it to look. Because it's a CSV file, it will ask me every time whether I want to save it or not after I close it, and I don't. So I'll open this script in RStudio now. And there's a lot of code here. There's a lot more code than the previous time when we were doing the BLE frequencies. But you don't need to worry about most of this code. So at the beginning here it says functions. And just to make this file a little bit easier to look at, I'm gonna, every time I see some line of code that says something with then an arrow and function, I'm gonna collapse all that code that comes after that, and I do that by hitting this little triangle here. And by doing that, a lot of the code collapses, so you can see that now the line goes from 5 to 15. And I can do that a couple of times at line 16, at line 35, at line 74, at line 96, at line 103, at line 122, and line 160. And what these are a lot of functions that the R script will use, but for now you don't really need to worry about what they're doing. So now our code looks already much smaller. And so the first thing we need to do is load a few R packages. Those are packages or libraries of functions, just as ones that I am defining here, but those functions are made by other people. And by loading these libraries, I will tell R, go and look in those libraries and look for, and know that I will use some of the functions that are in these that are not standardly available in R. And so I can just do that by selecting these two lines and hit run. And I'll get some warnings because my R version is newer than the one that these packages were developed under, but that's not an issue. If you get an error saying that you don't have those packages, that means you didn't install them. In that case, you have to go to Tools, Install Packages, make sure that this says install from the repository, and then here you can install the packages. And the name of the packages are the black part here, so that would be string, and so you can see already it show up here. And by hitting space after selecting the first one, you would be able to get the other one, and you can then say install. I'm not going to do that because they're already installed for me, but that's how you install a package if you haven't done that yet. Then we need to tell R what all these functions are. So I'll do that by just selecting everything and hitting run. And if that all goes well, then here on the right you see that now R has a bunch of functions saved and now knows what these functions are doing. So then we need to, the few things that you will have to look into and change is here is this line, as it says here in green, is saying this is for loading data files. So right now only this one is in black, don't worry about the other one. So this will load our data, and to do so we first need to tell R that we're in which folder we are working and in which folder to look for our files. So we do that by, on the top, going to under session, going to set working directory, and then saying set to source file location. And as I've mentioned before, what this does is saying look in the folder where this R script is saved in. And that's the reason that I save my CSV file into that same folder, so that now when I say look for this file, that R will know to look in that folder and it will find it in the same folder. So the other thing you may need to do in this script is make sure that where it says file equals, in my case parent_check.csv, is make sure that this file, that whatever this part is that I just highlight here, that is the name of the file. Now for me that should be okay. So I can just click anywhere in this line and then hit run, and it should run and it will load the data, and if that worked correctly it will become available here as genotype data, and it says it's 68 observations, so it's 68 individuals for this many variables. Other things in this R script was originally just written with Genome Studio in mind, and so possible alleles for A and B, but then as we did some more analysis we got null alleles, and now our assist files put C, G, and T in there. So what this line does is saying which are all the alleles that I can find, and actually I have to add two more, I and D. So I hit the double, I'll do that again. So I hit the double quote and RStudio will automatically make 2 for me, and then I just say it's the I, and so that will appear between the double quotes because it's telling R that this is like a string or a combination of characters, and so it will look now for a character I. And then I hit a comma and I hit double quote again, and then I say D, because those are the 2 other alleles that are in our file. And then I can just click anywhere in this line and say run, and then I will have identified, or I will have told R what all possible alleles are. Now the next 2 lines are saying what are missing genotypes, what are strings, or how does a missing genotype look like. And so in Genome Studio it's NC, which stands for no call. In assist output it's 2 dashes, and sometimes it could also be 2 zeros if you have some other files. The next line is saying what is a missing allele, and that is because sometimes they just use an N and you will get double N. So it could have just added double N here, but it just allows for a bit more flexibility by saying which are the missing genotypes and which are alleles used to indicate a missing allele, or which are the characters to indicate a missing allele. So if I want to run them at the same time, I just highlight both of them and I hit run. And now I want to do my parent check, and I hope this will work. But what this will do, this line of code will check all known pedigree. And so by just hitting run here, if this works well, it should start now saying I'm checking 4 individuals out of 68, I'm checking 7, and it will tell you how far along it is in checking all the individuals. and this should go relatively quickly. And what it will do in the script is what it really does. It's just counting how often each of these alleles occur, and it will compare that to parents. And there's a and so well for a parent to be for an individual to be a possible parent, at least one of the alleles it finds in the offspring it needs to have in the parent, and it does something similar for a parent combination as well, but it will never check it. It shouldn't check parent combinations if a parent combination already if it didn't work. And so for me right now this script stopped running, or it's done, and so it saved its results in this file, but because it's easier to look at it in Excel, the second line of code will write it to an Excel file, and this Excel file will be called parent check results. And so you can change this part to anything you like, and that will be the name of your file that gets written. So if I do that, I get it will be written to this file, and there is now a parent check results in this folder. And if I open that, it will give me the following results. It will show me for each individual what the reported parents were, how many parent-child errors there were with the first parent, how many parent-child errors there were with the second parent, and how many parent-child errors there were in total. And so now we can easily go and check and see what is working and what is not. And so as you already can see, there's here a few individuals that have a pretty high number. So to me, this is indicating that no, these two are not the parents of this individual. And the same goes for this individual here, which is, what was it, FR10 T98. So those parents seem to be wrong. I'd say that this number is also too high, 93. It's also too high. I actually know that these should be right, so I'm not 100% sure what is happening here. I think they should be right. So it might be actually that that one of these individuals is not what it should be. And then here for index, which our file set is Rainier RosBREED, this is also relatively high. So now we found which parents are working, which ones are not. So and so now we can go and update our files. And I will do that right now only for the input file of R. But ideally, we go back in and change it in all our records to make sure that we are not keeping errors in our data set. And so if I go back up here, the order that R reports it is the same order as the input file. So I can go in and FR9 T31. That seems to be wrong, so I'm going to replace those two with a dash because both parents seem to be wrong. Then FR10 T98 seem to be wrong, so I'm going to replace those two with a dash. And then as we go down, I will just, for now, accept these ones. So I'm going to say this is wrong. Then for where's index? Index only Rainier is wrong. Bing seems to be right because of the low number of errors that it has. So it's only going to delete Rainier. And that, I think there's one more that has relatively high number, 40. So remember I set up to 1%. I think we have about 2,000 SNPs in our data set. So that would be about 21 errors. So at this point, I think 40 is too high. And I will also remove this for now. And then I will save this file again, and right now this is an updated file, and I'll come back to this file very soon. I do want to show that there are other ways to do this as well. If you go to the backup files for today's session, so backup files, session 3, parent, and there's a folder called parent check Excel. Then there is a file named parent-child errors and parent-child errors. I can quickly show you how one can do it in Excel as well. Once the file opens. So what I have here is a very similar file which has all the genotypes for all the individuals and all the SNPs. So starting on row 3 and everything below row 3 is just the full data set that we're using. And then here on top is one individual, is the genotype of one individual that is copied right here. What I did in a second sheet is go and I have to go to the very beginning of this file. What I did here is for each of these cells there's a formula, and what the formula is doing is comparing genotypes from the first sheet. So what it is doing is checking, well, what is this and what is this genotype? And so in this case it's AA and here it's BB. Well, that would not work as a parent-child relationship. So at this point it returns me a 1. So what the formula is doing is saying if the first genotype is AA and the second is BB, or the other way around, if it's BB and the other one is AA, then return a 1 because it's one error. And if it isn't, then everything is fine, so return a 0. And then it does that for all individuals, and it compares all individuals against the one on the first row. And then here in this column, it summarizes how many errors were found. And so you can see that when you compare these two individuals, there's 196 errors. So at this point, we know that this cannot be a parent. So I can go and filter this column for anything that is pretty low. In this case, zeros and ones. And well, not surprisingly, I get the individual itself as zeros because everything would match. And then I would get one other individual that has only one error. So this could be a potential parent of this. And I could check with my pedigree to see whether that the parents in my pedigree do indeed get a low number of errors. And then if I do find that my two parents have a low number of errors, I can go to the second or the third sheet, and then where I paste the data of both the parents here in row 2 and 3, and I paste the genotype of the child, or what I think would be the child, in row 5, and then this formula checks the two combinations versus the child and then reports how many errors there are. And so in this case you see a lot of errors, so these two will not be the parent of this individual. But as you can see, this is a pretty long code because there's a lot of possible ways that things could not match. And this is only for A, B genotype. So the more possible alleles, the longer this formula will get. And so at that point, the R script can become really convenient. So this would be a way to look in Excel. Now, I'm not going to save this. If you have one parent known and the other parent missing, but you do have two of the grandparents, so you have the two parents of that missing parent, you can go and check if those grandparents match as well. And I'm going to quickly show a way to do that in Excel. And so in this case, we have the apple Honeycrisp, and we do know its two parents thanks to Nicholas Howard. And the first parent is Keepsake, and the second one is MN6027, which is a selection from the Minnesota breeding program, but this selection does not exist anymore. But we were able to figure out the two grandparents, or the two parents of this individual, and thus the two grandparents of Honeycrisp. Now, there's a way to confirm grandparents, and actually that works for parents as well, is by setting the offspring, the individual you want to check for its parents and grandparents, you select all the heterozygous SNPs in this case. And then we lock in the known parent, we lock in as being homozygous, either one, in this case, well, but one at a time. So in this case, homozygous A. And so that would mean that all these AB SNPs would have gotten the B allele from the other parent, because the first parent is AA. So for those SNPs, that parent could not have given the B allele. And so if you have the second parent, you could just go and check whether you truly have all, if all these SNPs truly have a B allele in here. Now we don't have the parent, we only have two grandparents. So in this case, I'm going to lock in one of the two grandparents as also being homozygous for A. And that would mean that this B allele cannot come from parent 1. It cannot come from grandparent 1. So it must come from grandparent 2. And if I now look at all these SNPs, I can see that yes, all of them are AB or BB, which is an indication that yes, this could be a grandparent. And so you could repeat this by setting this to BB and this to BB, and then this should all be AB or AA. And if you go ahead and try that, you will see that all of that will match, and that's a way to confirm grandparents. Now the last thing I want to talk about is finding parents, because we do want to find as many parent-child relationships as there are, and we can use the exact same R script for that. It uses the same principles as before, although now rather than just picking the two individuals and checking if they work, what we'll have to do is go and compare an individual with missing parents against everything in the data set. And I've already, when I was doing this in Excel, in this file here, you could already see that that was relatively straightforward. I would just filter for anything with a low number of errors, and that would become a potential or a possible parent. Now R does this as well. I will need to reload my genotype data because I've made some parents missing, and I want to figure out if I can find the right parents for those individuals. So I went into parent check and I made those parents missing in there. And so now I saved it, so now I'm going to reload that file, and I do that by hitting this line that is there for loading the data again, and it will update this file. And then I run this line of code. What it will do is look into genotype data, look for any individual that has a parent with at least one of the parents missing, and then we'll start comparing those individuals against the rest of the data set. Now the two other numbers here are how many errors do I allow for parent-child errors in the first case. So 30 might be a little bit high. Might be better to be 25 or 20. And then the second one is how many parent-child errors do I allow when looking for possible parent combinations. So I can go and hit run here. When I do that, if you have updated the R script file as I sent out an email about yesterday evening, then this should work. Otherwise, if you haven't yet, I've updated this R script on the Dropbox and so you should get the updated version, and then it will not produce any errors. And so what it will do now is it will first check for any individuals with a missing mother, then it will check for any individuals with a missing father, and then it will check for any individuals that have both of their parents missing. And this is going to take a while, and I'm not going to wait for this to end, because this is probably going to run like half an hour or more. But I can show you what the results look like from yesterday. So there are 2 files created. If quickly go back to R, once this has done running, I just run those 2 lines of code to write the results to CSV files. And so the first one is the find possible parent results. If I open that one, what it will do is just say, this is the individual I found, and this is a possible parent. Now, in this case, you need to know your germplasm a little bit, because, for instance, an unselected seedling is very unlikely to be the parent of a cultivar, especially if this unselected seedling was made way after the cultivar was already available. So some of these might not make sense, and for some of these it might actually be the other way around. Although the R script should remove any offspring from the individual when comparing it to the rest, because any offspring of an individual will also turn up as a possible parent. The other thing you see here is that Hedelfingen could be the parent of Hedelfingen. Well, the R script does filter out the individual itself, but because we have duplicates in here in our data set, it does identify the duplicate as a possible parent. So you might want to remove any duplicates before running the script. It will also make the script slightly faster, because it will have to compare an individual against less individuals. I'm not going to save this now. Then if there are 2 parents, if it either finds 2 possible parents, or it finds 1 possible parent and the other parent was already known, it will also check if the combination of the two possible parents works. And it will write those in the find possible crosses result, and that one should open. Okay, here it is. And so it will report all possible crosses it found. So it found that index where we removed Rainier as a parent, actually that Stella cross Bing works as 2 parents. Now, there's a few that say where the script says it cannot be tested, and that is because one of the parents was missing, the other parent was given. In our cases, it's Curation or Napoleon that was given, but Curation is not in our data set, and Napoleon, we removed it from our data set. So it does know the parent. I mean, it thinks it knows the parent because it's a given parent, but it cannot check if a combination is working because it doesn't have the genotype for that parent. Now, here, this individual had both of its parents made missing, and the R script figured out what the right parents could be, and we do know that this is indeed the right cross. And then finally, what you can see here is that Hedelfingen could be a cross of itself, basically. And the way the R script is written right now is allowing for self compatibility, but because for some of our crops it is possible. So I'll quickly go back to the R script, but I think it's still running. Yep, so it's still only checking for any individuals with missing fathers. It still has to go through all of this for any individual with both parents missing. So this is going to take a while. And so you can keep running this if you want, and then write the results to an Excel file and see what the results say. But I don't think it's we need to wait for it now. So I think that will be it for today. I do know that the R script is still a bit slow. I'm still trying to get it better. So at this point, we found individuals with low quality, individuals with unexpected ploidy. We removed unreliable SNPs, and we've updated our pedigree information. And so right now we're ready to go to the next step and find any remaining errors, actual errors in our genotype halls, which I will talk about next session. I do want to still point out that once we've updated the pedigree information, it's probably best to update it in the sample sheet and make a new Genome Studio project as well, because Genome Studio will otherwise still report things as errors when we know that they're not errors anymore. You might want to rerun assist, although when we're using the germplasm option in assist, Eric van der Weg has told me that it's actually not using pedigree information. So if you're using the germplasm option, then we probably won't get different results. But if you're using F1s or other options, you might get other results in assist. And then any other analysis we did, such as the B allele frequency, checking for ploidy, or sample quality, or checking for duplicates, they don't really need the pedigree, so we don't really need to go and redo those again. And I think that is it for today. So if there are no questions, then that will be it. I will compile the video and make it available probably tomorrow, or at least by the end of this week. Alright, so that was it. Thank you, guys.
Thank you.